Well, thanks very much. Um, I'm going to talk to you today about finding red supergiants in the local group and what these have taught us about massive star evolution. Um, this is work that has been done with Catherine Nugent and Emily Levesque. Of course, we have more collaborators than that, and I'd like to do a shout out to our four theoreticians, Jan Eldridge, who's responsible for the massive star binary models, BPASS, and George, Sylvia, and Cyril, who are responsible for the Geneva evolutionary models. So our goal is to understand massive star evolution as a function of metallicity. And our approach has been to identify complete samples of evolved massive stars throughout the star-forming galaxies of the local group. Now, you'll notice I put complete in quotes. And the reason for that is that I don't think you can have a complete sample of red supergiants to know a complete sample of red supergiants in the nearby galaxies. They would extend down to a luminosity of about 3.8 Dex. And around 4 or 4.3, you start getting totally swamped by the AGB component. And we'll talk more about that in a moment. The local group is a great place to do these experiments. We have the low metallicity Magellanic clouds. We have M33 with this wonderful metallicity gradient from the center to the outer pole. And we have the Andromeda galaxy, which has suprasolar metallicity. In writing proposals, we argue that we use evolved massive stars because they give us such a handle on testing evolutionary theory, such a lever on. But the actual reason is also that they're much easier to identify samples of than the unevolved massive stars. So when we do this work, we first identify a sample from near-infrared photometry. And the reason we use near-infrared photometry is we don't want to just find red supergiants, but we want to characterize red supergiants. We want to understand their effective temperatures and their luminosities. And so for this, the near-infrared is great because the effective temperatures and the all-important bolometric corrections are sensitive to the near-infrared colors. And of course, reddening corrections are much less of an issue. Then we have to clean the sample. We can remove foreground stars using Gaia, and we can make a first pass at removing AGB stars, at least for the brighter red supergiants, using a near-infrared color magnitude diagram, following the pioneering work of our good friend and colleague, Ming Yang. This is an example of what we do with Gaia data. We do a covariant analysis. This allows us not only to eliminate the objects that are clearly foreground stars and identify the stars that are clearly members, but it also lets us assign a probability of membership to the ones that are in between. This is an example of how well this works. This is in the Andromeda galaxy, in which we see on the left the red points are the ones that Gaia tells us are foreground. Then the black points are the ones that Gaia tells us are members. The green are the ones, well, we're not so sure about. And the blue are the ones for which there are no Gaia data. And you can see, however, how well the foreground stars match the prediction of these wonderful Bizicon Milky Way models in the direction of M31. Here is a color magnitude diagram of M31 in which we've identified the region of M30 of red supergiants. And I've indicated the lines of constant bolometric luminosity, 4.3 and 4.0. And again, red supergiants should extend all the way down to 3.8. But this region here is what Catherine and I came to call the triangle of shame. These are asymptotic giant branch stars. And you can see that they totally swamp the red supergiants by the time you get down to a luminosity a little bit below 4.3. So you can certainly make a list of red stars that extend down to deeper luminosities, but they're going to be badly contaminated by AGBs, I think, no matter what you do. How well this works is shown by the distribution of red supergiants in M31. On the left, we see the red supergiants fall, the distribution of the CO ring, where all the recent star formation is taking place. While on the right, we see the AGB stars were evenly distributed throughout the galaxy, which you would expect for such an older population. Here is the color magnitude diagram for the LMC. And we can see, after all, the reason that Ming's method works so well is that at lower metallicities, the Hayeshii limit is shifted to cooler temperatures. And so in a galaxy like the LMC, the AGB contamination is not quite as severe, and you can probably go down reliably to a luminosity of 4. But below that, you still are going to have significant AGB contamination. So it's good to understand your limitations. So I now like to turn to what the samples have actually taught us about massive star evolution. And I'm going to begin with the time-averaged mass loss rates. So our colleagues in Geneva like to say that this is actually the most important and the least constrained ingredient in massive star evolutionary models. You don't care in the models what the mass loss rate is of a red supergiant on Tuesday. What you care is how it behaves over the lifetime of the red supergiant. It is the most important because increased mass loss causes red supergiants to turn back towards the blue before core collapse. And so you depopulate the highest luminosity red supergiants as you have high mass loss. And it's the least constrained because, as we've heard, mass loss in red supergiants is primarily episodic. It can happen in great bursts when the outer layers exceed their Eddington luminosity, as in VY Canis Majoris. So to emphasize this, here is what the mass loss rates are, if you will, on a Tuesday from red supergiants in the LMC. And you can see that at a given luminosity, they basically span a range of 1,000 in their values. And the older evolutionary tracks used to adopt the de-Jaeger relation. And sure enough, if you look at this, it goes through some of the points. It's, it's not terrible. What the Geneva group did in 2012, however, was they used basically a modified version of the de-Jaeger relation. But whenever the outer layers of the star exceeded the Eddington limit by a factor of 5, they arbitrarily increased the mass loss rate by a factor of 3. So this line here is not a prescription that the Geneva group used. This is what you get if you take their time averaged, if you will, mass loss against luminosity. And the result of this was that a 20 solar mass red supergiant had 10 times more mass loss during its life than it would have if you didn't make this correction for what happens when the star exceeds the Eddington limit. George Manet has argued that the rate could be 10 or 25 times even higher than that based on the observations, while Emma Beezer would argue that the rates are already much, much too high. So who's right? And so one way we decided to approach this problem was we know that the red supergiant mass loss rate, time averaged, will have a huge effect on the expected luminosity function of red supergiants. High mass loss rates will depopulate the highest luminosity red supergiants. They'll spend much less time and they'll switch back over to the blue. So why not test theoretical luminosity functions against the actual ones? And so the Geneva group was kind enough to calculate for us models using a 10 times normal mass loss rate. And they also calculated what they would have gotten in 2012 if they had never made a correction for stars exceeding the Eddington limit. So this is now without the super Eddington correction. And again, these are time averaged values. So this is then what the predictions are, the percentage of high luminosity red supergiants, by which I mean more luminous than 5 Dex, versus what you use as a lower limit for the luminosity function. And what we can see, the blue on top, that is for the low mass loss rate with no super Eddington correction. The red is what they did in 2012. And then the magenta is what happens if you use 10 times the normal rate. So what do the data show? And the answer is that when you look at the luminosity function for M31, they in fact agree very well with the Geneva models from 2012. And this is now the solid points show the models with rotation, the dashed ones without, and they fall in between those two. So my takeaway from this is that significantly lower or higher time average mass loss rates can be ruled out. Secondly, what about the upper luminosity limits? Well, Humphreys and Davidson in 1979 published this plot showing that the luminosity of yellow and red supergiants was, the upper luminosity was nowhere near as high as what it was for OB stars. So what was stopping it? And we understand today that what happens is that as a star evolves, it cools, and as it cools, the opacity increases. As the opacity increases, radiation pressure increases, and mass loss increases, and the star turns around and goes to the blue and becomes a Wolf-Rayet star. And so the question is, at what point is that trough in this diagram? At what luminosity is that trough? And does that trough depend, where the location of that trough, does it depend on metallicity? And on the one hand, you could argue that at higher metallicities, the line opacity should be greater, and therefore that limit should be lower, while at lower metallicities, this limit should be higher. But Higgins and Vink have argued that there's a competing effect that's particularly important at low metallicities, and that is excess mixing in the superadiabatic outer layers, which will help keep the star compact. And so, and they predict that the limit shouldn't depend on metallicity and should be about 5.5. So when we look at all the data we have on the SMC, the LMC, M31, and M33, what we find is, in fact, the limit is 5.5, plus or minus 0.1 dex, and is regardless of metallicity, which I think is a really cool result. And other people have come to the same conclusion. Finally, I'd like to talk about the binary fraction of red supergiants. This was the PhD thesis of Catherine Nugent, and this is what a red supergiant and with a companion looks like. And Catherine argues that on theoretical and evolutionary grounds, you expect any companion of a red supergiant to be a B star. And indeed, that's what we've known for decades in terms of the dozen or so of red supergiant binaries known in the Milky Way. And you not only see the lines of titanium oxide, but in the blue, if you have good signal to noise spectra, you will see the upper Balmer lines, and those have to come from a hot companion. So what Catherine did was she took spectra of hundreds of Magellan Cloud red supergiants using the Magellan telescope. And there are only a few stars with published Galax photometry in the UV, but what she did was she downloaded 4,000 Galax images and actually set hard limits on what the UV flux was on these images for all the red supergiants in the sample. And then she applied this to machine learning K and N algorithms, applying them to UV photometry. So on the left here, we see the clean division between stars that don't show the Balmer lines and stars that do show the Balmer lines. And then you add in the ultraviolet fluxes and you apply this machine learning algorithm, and you can assign a probability to all the red supergiants that have photometry in the Magellan Clouds. And what she found was that the observed binary fraction is about 13.5%. Now you have to correct that, because when you happen to observe a red supergiant, it could be that it's in the eclipse, stays in the eclipse for a long time. So she used the BPASS models to correct for this. That adds another 3.6% that you would miss. And then what about the stars where the companions already turned into a compact, already turned into a neutron star or a black hole or something? So she used the BPASS models to correct for that. That's another 2%. So the final binary fraction she got is about 20% for the LMC. Now, this seems like a small number, right? Because we know OB stars have a binary fraction more like 70%. But in fact, it's exactly what you would expect. And the reason is, as a O star expands into a red supergiant phase, any close companions are going to merge. And sure enough, it's consistent with a BPASS merger rate of about 30%. And so if someone comes up with a higher binary fraction than this, you got a problem. Finally, And I'll note that similar results were found on the basis of radio velocity studies. Finally, she extended this to M31 and M33, finding that, in fact, the binary fraction was larger at supra-high metallicities. And this suggests that the distributions, the period distributions, the separation distributions for all B binaries at suprasolar metallicities has to be different than what it is in the Milky Way and in the Magellanic Clouds. So I know I'm out of time. I'll stop here and I'll just leave up my summary slide. Thank you very much.
Brilliant. Thanks, Phil.
Hi, Phil. Leen de Sint from KU Leuven. I have two questions. The first thing is something I have never realized, but you are saying that companions of red supergiants are most often are B-type stars. Why?
Well, I was so when we first started this, I didn't know anything about this. But in fact, if you look at the galactic, there's a dozen red supergiants in the Milky Way known to have companions. They're all B stars. So why is that? So if you consider this from an evolutionary point of view, first you have the question of how long does it take you to become a red supergiant? And at the same time, a lower mass star won't have finished forming by the time your first star has reached the red supergiant stage. So you're not going to have red supergiants with A star companions or F star companions. That just, it can't happen. And you could have O stars as companions, but they should be very few. And in fact, even though we found hundreds of red supergiant binaries, and when Catherine started, only this dozen were known, and now we know like 500 of these. They're all consistent with showing bomber lines that are like that of a B star, and not you don't see helium-2 showing up in the spectrum.
Yeah, okay, I got it. I never realized that, so thanks for explaining me.
I didn't either before we started working on this stuff.
And then the second question was on the last part of your talk. How has you then been calculating the merger rates? On what kind of assumptions has that been based? You were referring to some models, but...
Right. So this is buried in Jan Eldridge's BPASS code, and I frankly do not understand it. But what I do know is that if you take their predictions, that it matches what Catherine found, and that is based then on this merger rate of like 30%. And to me, this makes sense because I do know that most large fraction of OB binaries are closed systems. And so it's easy to imagine that as a star, the more massive star expands into a red supergiant stage, it's going to eat up the other star.
Yeah, but there is also the competing effect between mass loss rate and tidal effects.
Yes, absolutely. It's more complex than that. And I don't know how if or how Jan takes that into account.
Okay,
I agree that it's more complex than this.
Thanks.
Thank you.
Hello, thank you for a nice talk. And the first question, when you show the color magnitude diagram of the LMC, and it seems that the fin end of the red supergiant branch is down to the tip of the red giant branch. And in this CMD, it seems that the fin end of the RSG is extending down to below the tip RGB. So what this stars seems like.
Right. So what I think we see here is that as you go below a luminosity of about 4, you are in fact getting contamination from the AGB stars. If you look at the evolutionary tracks for LMC metallicities, you expect to see red supergiants down to a luminosity of about 3.8. And that's sort of consistent with, near the tip of the red giant branch, more or less.
Okay, thank you. And the second question is that actually the metallicity affects the distribution of RSGs. So in different galaxies, such as the SMC to the metal-rich M31, the sample of RSGs maybe distribute in different temperatures. So when we consider the mass loss rates from different samples of RSG, should we consider the effects of the metallicity?
Absolutely, and that's why for every galaxy that we've done, we've had to move where the red supergiant limits are, and it's pretty easy to see this from the upper ones, and then it gets a little bit dicier on exactly where you draw the line. But exactly as you say, in fact, for our work in NGC 6822 and our work in the SMC and the LMC and in different regions of M33 and throughout M31, we had to shift where the distribution, where we drew these lines and said, this is where the red supergiant. And we know this historically, right? Because just the average spectral type of a red supergiant in the Milky Way is like an M2 or an M3. Of course, it's based on titanium oxide lines, and some people don't believe that's telling you the temperature, but I do. And while in the Magellanic Clouds, a typical red supergiant is like a K star. It's not an M2. And the temperature is that where you find the red supergiants is going to be very much metallicity dependent. I completely agree. And that's why we have always taken that into account.
Okay, thank you very much.
Okay, thank you for your nice talk. I have a similar question in this plot that